Fourier series or Fourier series, sometimes this last R is not spoken because this is a name of a legend. So this is the Fourier series. This is a series just like the Taylor series and other series, but it solves a lot of problems. It takes you from one domain to another. So we have three different coefficients or weights, and the values or the expression for them also is there. So in order to understand all this, we need certain mathematics. We need to have a background. First is even and odd function. What is an even function? When we have f minus x, if you put minus x, the function becomes itself. When the function, if you put minus x, it will be negative of fx, that is going to be odd. Graphically, if I can tell you, even function is symmetric about the y-axis. Both sides you see, they are symmetric, they look same. The odd function is symmetric around the origin. If I just turn the right one to 180 degree or left one to 180 degree, this will become same. So this is the odd function. There are certain functions which are neither even nor odd as well, like you see here. So in order to have an example of an odd function, just take the odd powers of x with any coefficients. If you put negative x, it will be minus of fx. It will be minus of 5x cube minus 3x. If you put in the even function negative x, the same function will come. In the even and odd functions, it's very important to talk about sin x and cos x, because these are the base of the Fourier series. You have seen there is a sine term and a cos term. So sin x is an odd function and cos x is even function. If you put sine and negative x, you will get negative of sin x. That is, it is odd. Cos negative x is in fact cos x only. That is why it is an even function. Sin x odd, cos x even. Now, let us say that this odd function is negative, cos x is positive, and you know how to multiply the negative positive? Same thing here. If we have two odd functions, negative, negative, x is negative, sin x is negative, it will give you even. Negative, negative is positive. If you have two even function, one is positive, the other is positive, you will get a positive, that is an even function. But if one is even, another is odd, that is this cos x is even function, sin x is odd function. If you multiply it, what do you get? Negative, that is the odd function. This is going to be used a lot. One more explanation regarding the integration, because this is the key part of Fourier series. Now if you have an integration is nothing but addition from negative p to p, or you can say minus pi to pi, like this, minus 1 to 1, minus 2 to plus 2. So this is function. So as I said, this function is an odd function. That means odd function means it is symmetric around origin. That is, if you turn it 180 degree, they will be same. So if one is a, other is minus a, if you add them, a minus a is 0. So this negative p to p integration of fx dx will always be 0, because they are having the magnitude same, but the direction is different. Now when you seriously talk about this in the even case, then even functions are symmetric. That is, if one is area A, the other will be area A. If you take the integration from negative to p to p, that is minus pi to pi or minus 2 to 2, like this, it will be adding. Integration is just adding. So you're adding these two areas. This will be 2a. Same thing will be used here, that if you have a function which is the even function from negative p to p, fx dx will give you twice, you can write it as twice of 0 to p, and this will be fx dx. This also we are going to use in the Fourier series most of the time. Now coming to periodic functions. Now the main key of going to a Fourier series is that we assume the function to be periodic function. What is the periodic function? Why do you want a periodic function? Why do you want to turn an algebraic function or any function into this kind of function? The periodic function is repeated. It has a period after which it repeats itself. For example, if we have function fx, if I add a t, capital T, that function is again regained. That is, that capital T is the period because it is repeating. So the period function is actually showing you repetitive behavior. You make one part of it and then just replicate it. It will be same function. So the period, after every period, it will repeat. Now coming to sine and cos. Sine and cos, they both are periodic functions. They are periodic expressions. So the period is 2 pi. See here. This is sine x. So here you have 0 to 2 pi again. How do you know the period? From where it takes a turn and again start taking that turn. That is, this 0 to 2 pi is the period. Similar explanation can be given for cos x as well. Now if I make this as pi x, if I took pi from here, the period will be 2. And if L is any fixed number, take any fixed number, then sine 2 pi x divided by that L, this sin x and cos x with 2 pi x L as inside this function, the period will be L. It can be P, it can be L, any letter you can choose. So it is 2L. I'll just explain you in the example. That period is taken as 2L. So this is periodic function. Fourier series. Fourier series is this function or expression. Here you see John Baptiste Fourier. He made this. He developed this. So the main key is the cosine and sine. Any function, algebraic or any, can be converted to sine and cosine. That is, any voltage or current. These are values. Now this has to be converted into some other domain, say frequency domain. Because if something is in spatial domain or time domain, we are not able to understand it more. But if you turn it to frequency domain, you will be able to find out more out of it. So this expression is actually converting the space or time domain to the frequency domain. So this cos and sine is specifically meant for it. So a Fourier series, you can define it as the expansion of periodic function fx in terms of what? Infinite sum of sine functions and the cosine functions. It is infinite. See, sigma n equals n to infinity. So this Fourier series, you see sine, wherever it is 0, cos is 1. And whenever cos is 1, sine is 0. Likewise. So they are kind of orthogonal. You can say 90-degree turn. So Fourier series makes use of orthogonality relationship of sine and cosine function. So let us take an example, simple example of an image. An image has pixels, brightness values. Now these brightness values are values, just values. So a big image will have multiple of these values. So why not to change it into the frequency domain? Because right now it is in the spatial domain. It is just a grid. It is just a table. Now converting it to frequency domain, now you can have a wide range of application in this Fourier transform domain. That can be image analysis, that can be image filtering, image reconstruction, image compression, all in image processing. Coming to data communication, Fourier series is used in this data communication. As I said, voltage and current, how to change them, how to better analyze this. We can convert from the original domain to this frequency domain, and then we can analyze basically waveform to the bit and bit to wavefront. Fourier series, this is the expression. Now let us take any value p and a function fx. This function is a periodic function. Now let us say we are taking it from negative pi to pi. negative pi to pi. Let us say this pi is p. We are taking p any arbitrary range. So minus p to p because we are taking piecewise. So negative p to p, which is actually range is 2p, because minus p to 0 and 0 to p is 2p only. So period 2p, you see here p will be, it has to be, L has to be 2p, then only we get a 2p is equals to 2L. So we are taking this p as pi here. If you take negative pi to pi, it can be minus 2 to 2. So p will be 2. So this series is having cos and sine term, and this is a constant a0 by 2. Sometimes you will see c also. So this is c by 2. So for first coefficient an has cos term, bn coefficient has sine term. So a constant, a cos term and a sine term. So this a0, because it is very easy to find out these value an, bn and a0, just multiply whole of the function with cosine term, whole term with sine term. This is the way some of the part will be cancelled, and you will get a0, an and bn. We are not going into that detail, but it is very easy to find out this a0, an and bn. So now you see the expression. Every expression is integral from negative p to p. For example, you are going to minus pi to pi, or minus 1 to 1, or 2 to 2. So this p is actually this value. And then we have three different coefficient, and these weights will tell you which part is having a more weight, which is lower weight. And that will make a waveform, and that waveform will be a Fourier series waveform. So before we go to the actual example, there are useful identities which we will use. Sine n pi is 0. Sine 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 20 pi, 400 pi, it's 0. So whenever you get sine n pi, just put it as 0. When we have cos n pi, that is any number of cos pi, cos 3 pi, cos 5 pi, any. If it is odd, it is negative 1. Minus 1 to the power 1. Because cos n pi is negative 1 to the power n. And if you have odd, you will get minus 1. If you have even, you just get 1. So just write this. Sin n pi 0, cos n pi equals negative 1 to the power n. And depending upon even and odd, you will write the term as negative 1 and 1. One more important aspect of this Fourier series is depending upon even and odd function. If fx is the even function, with even function, if you take this bn coefficient, fx is even function. If we say that we are dealing with even function, sine is odd function, and plus and minus, what do you get? Negative, that is the odd function. So inside you will get an odd function. From negative p to p odd function will always give you a 0. So bn will become 0. Whenever you are dealing with even function, just forget about bn, you just have to find out a0 and an. Then if fx is odd, if it is odd, see odd function, negative p to p or negative any value x to x will be 0. Because a0 is what? Fx dx. Fx is an odd function, so this will give you 0. a0 will not be there. An, fx is odd and cos part is even, so it will give you negative. That is odd function. Again, the integral from minus p to p or minus x to x will give you 0. So when you have an odd function, a0 and an, just forget it. You just have to compute bn. Now this is the example. Let us say that fx is a periodic function and the one period is defined by this formula, this expression. This is piecewise linear. We are dealing with periodic function, piecewise linear, and then we are going to integrate it what the Fourier series says. So Fourier analysis, Fourier transform, the Fourier series, this discrete Fourier transform, the fast Fourier transform, all these are there. And they are based on all these concepts which we just saw. Right? Okay. FFT and DFT, they have difference in the complexity. FFT runs quite faster. Okay, this is the question. Now how do we find out? How does the signal looks? First, we have two piecewise functions here, part of function. Negative 2 to 0. So negative 2 is this, 0 is this. And 0 to 2, this is second part, second piece, 0 to 2. So between negative to 2, 0 is negative 1. So let us go to the y-axis and negative 1. So minus 2 to 0, just make a line. This is a green line. Now 0 to 2, again it's 1. So at 1, y1, you make a line. So how does this is being made? If you increase it, you see this is a black line on these two sides. So this is the piecewise, and as I said, this is period. So this period will replicate itself. That is why it is periodic. This is the second part if you increase the period. Now, as I told you, this fx is an odd function. You saw that is the odd function. If I turn it to 180 degree, it will be odd. So a0 and an will not be there. Only these two terms, forget it. Only bn we have to compute. Bn is what? This is 1 by p, negative p to p, fx sine n pi x by p. So this p you will see in various discussions, capital L also. Same thing. See, this is negative p to p. If I take from minus pi to pi, p is pi because the range is 2 pi. L is 2 pi. So that is, you have to take it because it is from negative 2 to 0 and 0 to 2. Actually, we are taking it from negative 2 to 2. So the p is 2 here. So fx is, let me write fx. I am not writing full sine, just sine dx. Sine is having n pi x by 2 inside. Now, I am just trying to show you that this is an even function. So just take 2 outside, 0 to 2, and fx, and again sine, I am not writing inside, sine dx. Now what I am trying to do here is, fx in between 0 to 2 is what? See, 1, in the question is given. So 0 to 2, this goes, fx is already 1, the sine, now I am writing full, n pi x by 2 dx. Sine you can do it. I hope that you know this a cos term will come, then inside n pi x you will do, and then you will apply the limit 0 and 2. So the final what you get is, I have written here 2 by n pi, 1 minus cos n pi. But I told you cos n pi is negative 1 to the power n. If you remember, this is negative 1 to the power n. This whole term is bn. Now go to the Fourier series and put it, because the term is fx equals a0 term you are not going to take, an term you are not going to take. You are going to take sigma n from 1 to infinity, bn in place of bn you will write directly this term, and then sine n pi x by p. Now you see negative 1 to the power n, 1 minus negative 1 to the power n, I am putting n equals 1. What do you get? 1 minus of minus 1, that is 2 you will get. So if I put an odd power of n, I will get 2. But if I put an even power, just put say 2. Or say, I am writing an even number. So 1 minus of 2, that is going to be 1 minus, this is 1 minus 1 is 0. So if I put odd, all terms will be 0. So it makes more easy. All the even terms you are not going to take. You will only see the odd term here. Even there is no term. So I am just putting it here, 4 by pi. So I am writing the n equals 1. So you get 2 by, I am writing in the actual term n equal 1, 2 by pi, 2 sine, and of course this 1 minus of minus 1 to the power 1 n is 2, this sine n is 1, so you get sine pi x by 2. So 4 by pi sine pi x by 2, this is n equals 1. Now you can also write n equals 3, then n equals 5, n equals 7 like this. 2, 4 will not come. I hope you got the idea. This is how we compute. There is one more explanation which I want to give here, is when you take n equals 1, 1 term, n equals 1 and 3, 2 terms. Likewise, if you take say 4, 10, 20, 30, 40 terms, then you see that this particular expression has given you the same figure, same geometric figure which we started from. Remember, this is negative 2 to 0, it was a term negative 1, and same 0 to 2 it was 1. So actual value came. This is all about Fourier series. Thank you so much.